dive into the two main types of sorting, horizontal and vertical, and discuss how each approach organizes and distributes data. When implementing database sorting, choosing the right strategy is critical for optimizing performance, managing data efficiently, and ensuring system reliability. While sorting offers significant advantages, it also introduces several challenges that needs to be carefully addressed. Now, let's talk about the best practices that ensure effective sorting. To harness the full potential of sorting while minimizing its challenges, following best practices is essential. Alright, so sorting is basically widely used in various industries, addressing unique challenges in data management and scalability. Hi everyone, and welcome to Prep Train, your one-stop destination for mastering skills in software engineering, backend development, and so much more. I am Sahib Kumar, and I am super excited to have you here join me today. At Prep Train, our mission is simple: to help you grow your technical expertise and stay ahead in your career. Whether you are a student or gearing up for your interviews, or a professional looking to deepen your knowledge, we are here to make your learning not just informative but also practical and more fun. Okay, let me ask you this. Have you ever wondered how apps like Instagram, Netflix, or Facebook basically handles millions of users seamlessly, or how they manage their colossal amount of data without slowing down? Today, we are diving into a fascinating topic that's behind the scalability of these massive platforms: database sorting. Database sorting isn't just some technical jargon, it's a game changer for building scalable and high performance system. In this video, we will break it down into simple terms. You will learn what sorting is, why it is crucial for modern applications, and how it can be implemented to optimize system performances. And trust me, it's going to be worth your time, because this concept is a must know for any backend engineer or aspiring tech professional. Before we dive in, make sure that you hit that subscribe button and turn on the notification. This way you will never miss out on any of our deep dives into essential tech topics. Also, if you find the video helpful, give it a thumbs up. It really helps us grow and brings you even more quality content. Also, don't forget to join our Prep Train Telegram community for latest job and internship updates, opportunities, and even more learning resources. The link you can find in the bio of this channel. Alright, so let me just grab my deck, and then we will dive deeper into the world of database sorting. Before diving into database sorting, it's essential to understand the fundamental concept of a database. A database is a structured system designed to store, organize, and retrieve data efficiently. Think of it as the backbone of modern digital systems, powering everything from e-commerce website to social media platforms and even critical services like banking and healthcare. To make this concept relatable, imagine a library catalog. A library basically has thousands or sometimes millions of books organized into different categories like fiction, history, or science. Each book has specific information: title, author, publication date, just like data entries in a database. The library catalog, whether physical or digital, serves as the database for managing all of this information. It allows librarians and visitors to quickly locate any book, just as a database enables applications to retrieve specific information from vast datasets. Now, consider the challenge of scaling. So, let's say a small neighborhood library where the number of books are too small. So, the librarian basically can manage its catalog manually, but what will happen when you deal with the scale of a national or global library system? You need a way so that you can distribute and manage the information effectively. And basically, users across different regions can access the books quickly and reliably. This is where database sorting becomes relevant. In essence, sorting is like dividing the catalog into smaller, manageable parts based on certain criteria, let's say like genre or reason, and storing them into different location. So this ensures that system remains efficient and scalable even as the number of users and data grows. This foundational understanding of database will help us appreciate the importance and mechanics of sorting. Now that we have established what a database and database sorting is, let's move on to the next slide to explore the concept of horizontal and vertical sorting in more detail. Okay, let's dive into the two main types of sorting, horizontal and vertical, and discuss how each approach organizes and distributes data. Database sorting can broadly categorized into two types: horizontal sorting and vertical sorting. Each approach addresses different needs based on how data is organized and accessed. Horizontal sorting involves splitting data rows into multiple sorts. So each sort contains the same schema, but the actual data differs. For example, consider a customer database with millions of users. So in horizontal sorting, customer with IDs 1 2000 might go into one sort, 1000 to 2000 might go into another, and so on. This approach is ideal for handling large data set where rows grow significantly over time. So it distributes the load evenly and it ensures that no single server becomes a bottleneck. Horizontal sorting is widely used in applications like social media platforms or e-commerce systems where user specific data is vast and distributed. Vertical sorting, on the other hand, divides the database by columns, so each sard contains a subset of the schema. For example, in an e-commerce database, one sard might store product information, example, let's say names and prices, while another one handles customer details, example, let's say address and orders. So this approach is useful when different type of data have distinct access pattern. For instance, product information might be queried frequently, whereas customer data might involve more sensitive information. By separating them, you can actually optimize storage and query performance for each type of data. While both methods offer scalability, their effectiveness depend on the specific requirement of the application. Horizontal sorting excels in basically scenarios with high row growth, while vertical sorting basically suits systems where data types vary significantly. A clear understanding of these differences will help us make informed decisions about which strategy to employ in a real world scenario. Okay, now let's move forward to discuss the key benefits of implementing sorting in modern systems. Okay, so let's focus on the advantage that sorting brings basically to the database system. Sorting brings several critical benefits, let's say like boost performance. So by distributing data across multiple servers, query execution basically speeds up because no single server has to handle the entire node. Secondly, we can say it also enhances scalability. So horizontal scaling is possible as more shards can be added to the system to accommodate growth. This is particularly beneficial for applications experiencing exponential data growth. It also ensures high availability. So even if one shard fails, the rest of the system continues to operate, minimizing downtime and maintaining services. So having explored the benefits, let's move on to the next slide where we will differentiate basically between sharding and partitioning to clarify these two different concepts. It's important to differentiate between sharding and partitioning as they are often confused. Sharding basically distributes data across multiple servers. It's a technique for horizontal scaling in distributed system. For example, user data for different region might be stored on separate servers. Partitioning, on the other hand, basically organizes data logically within a single database. It is more about structuring data into segments within a single system, like dividing sales data by region in one server. So the focus of sorting is achieving horizontal scaling by creating a distributed architecture, which is essential for handling large scale application. With these distinction clear, let's transition to the next slide and we will explore the various strategies used to implement sorting effectively. When implementing database sharding, choosing the right strategy is critical for optimizing performance, managing data efficiently, and ensuring system reliability. Let's dive into three widely used strategies and discuss how each one works to optimize database performance. The first one is range-based sharding. So in this approach, data is distributed across shards based on value ranges in a specific attribute, let's say date or ID. For example, all users with IDs between 1 and 1000 could go into one shard, while those between 1001 and 2000 are stored in another. This strategy is excellent for range queries and is often used in systems that require data archiving, such as logging systems. However, a major drawback is the risk of uneven shard size if the data distribution is basically skewed. For instance, if recent dates are queried more frequently, certain shards may experience basically higher loads. Next, we also have hash based sorting. So here is a basically a hash function is applied on the attribute, let's say a user ID, and the output basically determines the shard where the data will be stored. So this strategy ensures an even distribution of data across shard, minimizing basically the hotspots and load imbalances. However, hash-based sorting possesses challenges as for range queries where data is basically distributed non-sequentially, so it is very difficult to query over data. Additionally, when adding or removing shards, significant rebalancing might be required to maintain the distribution. We also have something called as geo-based sharding, where data is distributed based on geographic locations. For example, user data from Europe might be stored on servers in Europe, while data from Asia is stored on servers in Asia. This strategy is ideal for reducing latency as data is physically closer to the end user. It also supports disaster recovery by maintaining geographical redundancy. However, its implementation can be complex and requiring precise planning to manage overlapping or irregular access pattern. Each strategy basically has its strength and challenges, and the choice totally depends on the specific need of the application, such as query pattern, data distribution, and expected growth. Now that we have basically covered these sharding strategies, let's move on and discuss the challenges that come with sharding and how we can address them. While sharding offers significant advantages, it also introduces several challenges that needs to be carefully addressed. So first of all, let's say complexity. So sharding is not simple task. Planning the architecture, choosing the right sharding key, and maintaining the system requires a deep understanding for the application data and query patterns. Developers must account for how data grows over time and design the system to accommodate changes without disrupting the operations. This planning can be time consuming and it requires expertise in distributed systems. Secondly, we can say cross-shard queries. So in a sharded system, basically data that would traditionally reside in a single table might be spread across multiple shards. So queries that span multiple shards, such as joins or aggregation, becomes computationally expensive and it can lead to higher latencies. To mitigate this, techniques like query federation or denormalization are often used, but these solutions can complicate the database schema and application logic. Third, we have rebalancing. So as data grows, basically the distribution across shards can become uneven. So it leads to performance bottleneck, and adding or removing shards to address this required rebalancing, which involves, let's say, redistributing data between the shards. So this process can be resource intensive and it may temporarily affect the system performance, especially if done during peak usage. We also have problem with let's say data consistency. So maintaining data consistency across shards is challenging, especially in transactional systems where operations spans multiple shards. So ensuring that asset properties require an additional mechanism such as distributed transaction or eventual consistency, which can impact performance. We can also have single point of failure. So centralized components such as metadata services that manage shard mappings introduce potential single point of failure. So if these services go down, the entire system could be disrupted. Despite these challenges, adapting best practices such as careful selection of sharding keys, regular monitoring, and proactive planning, this can mitigate basically most of the issues. With the understanding of the challenges, let's move forward to the next slide where we will discuss best practices for implementing sharding successfully. Now, let's talk about the best practices that ensure effective sharding. To harness the full potential of sharding while minimizing its challenges, following best practices is essential. Let's examine these practices in detail. So, first of all, let's say choosing effective staging keys. The sharding key basically determines how data is distributed across shard. Selecting the right key is critical to avoid imbalances and hotspots. A good sharding key should evenly distribute data and align with query patterns. So, for example, let's say if more queries are filtered data by user ID, using this as a sharding key ensures that queries are basically routed to appropriate shard without scanning the entire system. Conversely, let's say poorly chosen keys can lead to uneven shard sizes and performance issue. Second, we can say that we should optimize basically cross-sart queries. So to address the challenges of cross-sart queries, consider techniques such as query federation, which routes queries to the relevant sart, or denormalization, which stores redundant data to basically reduce cross-sart dependency. Additionally, understanding query patterns and pre-computing frequently needed data can significantly reduce query latencies. We also should basically monitor the SARD health regularly. So continuous monitoring is basically crucial for detecting and resolving performance bottlenecks. So using tools basically to track metrics such as query execution time, SARD sizes, and server loads, we can actually implement alerts for abnormal activity such as unexpectedly large SARD or high latency in a specific region. So regular audits can also help identify the need for rebalancing or scaling. Next, we can also implement consistent hashing. So consistent hashing basically minimizes the data movement when adding or removing SARD. So it enables a smooth scaling. This technique helps maintain system stability and it reduces downtime during rebalancing. uh, One more thing that we can say is we can plan for scalability. So sharding system basically should be designed with future growth in mind, anticipating basically data growth, and ensure that architecture can be accommodated without additional shard and without significant changes. So incorporating scalability into the initial design pattern can helps for disruptive changes later on. So by following these best practices, organization can basically maximize the benefit for sharding while minimizing operational challenges. So after covering these best practices, let's move on to the next slide to explore real world application of sharding in various industries. All right. So sharding is basically a widely used in various industries, addressing unique challenges in data management and scalability. So let's explore a few key application. Social media platforms, let's say, they generate massive amounts of user generated content, including post, comment, and media uploads. Sharding basically enables these platforms to handle high volume of data and traffic by distributing user data across multiple shard. For example, a platform might shard data based on user ID, ensuring that content from millions of users is managed efficiently. This approach also enhances availability, as the failure of one shard does not affect the entire platform. Secondly, let's say e-commerce platforms. So e-commerce system basically manage large data set, including product catalog, order history, and customer profile. So during peak shopping seasons such as holidays, so these systems experience high traffic. Sharding basically allows for horizontal scaling, ensuring that the platform can handle surges in traffic without compromising security. Geo-sharding is particularly beneficial for global e-commerce companies, as it reduces latency by storing data closer to the regional customer. We can also say about let's say IoT platforms. So IoT platforms basically processes real-time telemetry data from millions of devices such as smart sensor, vehicles, and appliances. Sharding basically helps this platform handle high ingestion rates and ensures that analytics queries basically run efficiently. For instance, the data might be sharded by device IDs or geographic location, so it enables a quick retrieval of relevant information. Let's talk about gaming applications. So multiplayer online games require low latency access to player data and game states. So sharding basically supports this requirement by distributing player data across multiple shard, often based on, let's say, region or player ID. So this ensures that a seamless gaming experience for users is present worldwide. Last, we can say, like, let's say, financial services. So sharding is basically used to manage transactional data securely and efficiently. For example, let's say a banking system might shard data by account number, ensuring high availability and performance even during peak hours. By addressing the unique data management needs of this application, sharding basically supports scalability, performance, and reliability. Next, let's summarize all of the things that we have basically learned in this whole video. Now that we have seen where sharding is applied, so let's move on to the final slide basically to summarize the key takeaways from today's discussion. So today we basically discussed that database sharding is an indispensable tool in modern database architecture, especially for system dealing with large volume of data and high user traffic. And basically it's essential for scalability because sharding allows databases to scale horizontally, which is a necessity in an era where data grows exponentially. By distributing data across multiple shards, organization can basically meet the demand of modern applications without the need for high-end costing, basically costly servers. So scalability also ensures that systems can grow alongside businesses need, and it makes sharding a future proof solution. With sharding, basically the benefits outweigh challenges. While sharding introduces complexity in terms of implementation and management, the benefits far exceed those challenges. Improved performance, reduced latency, and high availability make sharding a valuable asset for applications requiring real-time data access and fault tolerance. Moreover, the ability to distribute data geographically basically ensures a seamless user experience across different regions. Sharding also requires careful planning. So basically, sharding is not just one size fits all solution. It demands a deep understanding of system requirement and access patterns. Careful selection of the sharding key, strategic planning for scalability, and consistent monitoring are all essential to harness sharding full potential. Without planning, sharding can lead to issues like uneven data distribution or difficulty in managing cross-site queries. Sharding is one of the foundation key for modern applications because application in industries, let's say like e-commerce, social media, gaming, and financial services rely heavily on sharding to maintain performance and reliability. It has become a cornerstone of database architecture, enabling organizations to handle global user bases and large-scale data operation efficiently. As we conclude, basically remember that while sharding demands significant effort during the initial setup, its long-term benefits in terms of scalability, performance, and resilience makes it an indispensable approach for modern applications. And that's a wrap, everyone. Thank you so much for sticking with me till the end of this video on database sharding. Today we explored what sharding is, how it works, and why it is a critical concept for building a scalable and reliable system. I hope that you found the explanation and real world example helpful in making this concept crystal clear. If you enjoyed the video and found it insightful, please give it a big thumbs up, and it really motivates us to keep creating content that helps you grow. And also don't forget to subscribe to Prep Train and hit that notification bell so that you never miss out on future uploads. Also, we would love to have you part of our growing community. Join the Prep Train Telegram community for latest job updates and internships and everything tech related. It's a great place to stay connected and keep learning. Thanks again for watching. I am Sahib Kumar, and I will see you in some other video where we will dive into even more exciting backend engineering topics. And until then, keep learning, stay curious, and take care.